Um, Hello, everybody, and welcome to VSAONLINE. So today we have a pleasure of having Wilkie Olin-Ammentorp with us from UC San Diego. So without any further delay, I leave the floor to you, Wilkie. So please go ahead.
All right, great. Thanks, Evgeny, for the introduction and the invitation. So today I'm going to be talking about some of the developments we've had recently in trying to integrate standard neural architectures, and particularly in this case for the one specific vector symbolic architecture, the Fourier holographic reduced representation. So just as an outline, we're going to go through some basic introductory material, which you're all probably very familiar with. Then I'm going to introduce how we've constructed residual layers for vector symbols specifically, and then how we can also apply some methods to compute self and cross attention with symbols, and then a conclusion to wrap it all up. So, as probably everyone in the group knows, vector symbolic architectures are kind of a unique approach to computing, I think, and they offer a lot of opportunities to compute very advanced queries on complex objects, but using kind of a simple architecture. And a lot of the impressive work that people have carried out uses all the tools that we have in vector symbolic architectures, that contains similarity between vectors, bundling vectors and binding them, and also sometimes the permutation or a protection operation. I think something that a lot of people are getting interested in now is adding sort of learnable mappings between symbols to this one toolbox that we use to manipulate vector symbols. And beyond just a simple mapping of one symbol to another symbol that we can learn, I'd like to make these mappings compatible with sets of symbols. So taking groups of symbols and being able to map them to a single or a couple symbols that are at the output. And we'd also like to make this computation compatible with neuromorphic systems. So if you can imagine that you want some specialized chip to handle vector symbolic primitives, you don't want to say, okay, now we need to have some CUDA core on the side to actually implement the neural network. We kind of like to keep everything on a common sort of domain to keep it all within a vector symbolic architecture. So to achieve these goals, this work focuses on using just the Fourier holographic reduced representation. And since that's quite a long thing to say, I'll just call it the FHRR for the rest of the presentation. So just as a refresher, each symbol is a long vector. And here we use a minimum of at least 1,024 elements. And the basic measure of similarity between these hyperdimensional symbols sort of is a metric that shows how close they are. So if two symbols are completely identical, the similarity will be 1. And if they represent completely different things, the similarity will be 0. Now, the other two common operations are bundling. Given a set of symbols, we produce an output symbol, which is similar as possible to each of its inputs, and binding, that given a set of symbols, you sort of displace them according to another symbol, and each of the outputs will be dissimilar to its original self, but the similarities between all of those inputs will be maintained after the transformation. So to go into how each of these specifically works in the FHRR VSA, each element of the vector we use as the number between -1 and 1. So in this case, it's an angle, but it's normalized by a radian. And that just kind of keeps everything on this convenient -1 to 1 domain, and we can kind of throw out a lot of pi's along the way. And so now in the FHRR, the similarity measure is the cosine of the difference between each angle in the vector, and then you take the average of all those cosines. When you go to do bundling, you can convert each of those angles to this complex representation by Euler's identity. You can sum each of those complex numbers, and then once you take the angle of that resultant complex number, you get the bundled output. And then finally for binding, you essentially take the input vector and you advance all of its angles by the second vector. So here, we have this input vector here with one of its angles in blue, and we have the amount we'd like to shift it by in the second vector. And so you just add that angle and it becomes a new angle on the domain. So all of these operations in the FHRR are kind of very nice and quick, and we can implement them in any number of programming languages efficiently. So now, when we talk about mapping symbols, what I mean by that is that this has allowed researchers begin experimenting with kind of new functions in vector symbolic systems. So we can do things like take a symbol as an input and produce another symbol maybe in another domain we're considering as an output. And ideally, the nice thing about using a neural network to do this is that new symbols that we have from a test set will correctly generalize on the mapping we want to learn. So that if you imagine, given a set of symbols that represent a test image set, we can have some mapping which will produce a symbol that represents its correct label. One of the things that neural networks can also do is that they can convert between domains. So example, we have on the bottom here, we have this real valued image from the MNIST test set. We can make a neural network that converts it into a symbol on the Fourier holographic domain. And one of the things that we and other people have shown is that the FHRR has a unique potential for neuromorphic implementations. So we'll get into the details of that a little bit later. But for now, as an example of one of the things we have done with this mapping of symbols is that we've created this architecture we called a bridge architecture. And the main concept behind this is that we use a neural network mapping to add or remove the information you expect between different sensory domains. So here on the left, we have the image domain that represents something an animal might see. And on the right, you have this label vector, which represents the sort of the concept that it wants to associate with. So here, we just use these code book of labels, but we would like to ultimately expand this to represent in different sensory domains. So something like the sound of someone pronouncing 1 or 2 to match the image. And that's something we were hoping to work towards with some of the work that we present in this presentation. So one of the nice things that we get out of this architecture is that once you can take this image and this label and convert them into symbols, you can then use the neural network that we have here to predict what it's going to look like when you just bundle these two symbols together. So when you have the symbol from the image one and the label symbol, you can just bundle them together to get this fused representation. And what the neural networks here do is they learn to predict what that bundled symbol will look like, and they can add or remove that information. So now once that training process is done, classification and generation really become two different modes of operation that this network can do. So you can imagine if you have a missing image, you can generate that image by taking the label 1, adding some noise, and passing it through the other side of the network, and you can get this generated image. And on the other hand, when you want to do classification, you have an image with a missing label. So you run this image through the left side of the network, and the right side can predict the label for classification. So this slide summarizes the results we see from this architecture where we run it on FashionMNIST. And so this is kind of the classification mode I mentioned, where you have this missing label that you're predicting, and after it goes through this training process where each side minimizes the losses between what it expects to see and what it actually sees on the training set, the test set generalizes well to predict the correct label for the images. And we show that the bundling operation is necessary to do this well for a given dimensionality of the sort of latent space in the middle. If you just have a control network that doesn't use the bundling operation, it performs much worse than the vector symbolic equivalent. And here we have some generated images where they're they're not great images, frankly. They're much worse than a variational autoencoder or something equivalent, but they produce kind of the correct average modes that you'd expect to see from the different clothing classes. So here, you can see that this kind of has the average shape of a shoe. Here we have the average shade of a shirt. And even for these low quality generated images, one of the things you can do is that from the middle of the network, you can sort of save the symbols that are fused and use those to self-distill the network. So you can save pairs of symbols from all the sides of the network, and given the same initial weights of the network, you can use those to retrain it down to high performance. So that's something which can be used for some continual learning. And we've shown there's a class incremental MNIST where it can do better than some other methods which don't really adapt well to the class incremental setting. So we're happy with those results as kind of an initial case, but we'd like to scale up the network to, as I mentioned, do more complex things than just the MNIST and FashionMNIST. And to get to those more complex tasks, we need more powerful neural networks to do the mappings between symbols. We were kind of seeing some of the limits between the simple networks that we use in the bridge networks, which are just kind of autoencoders, really. And so the question that we were kind of left with at the end of that research was, what neural architectures will be good for processing, vector symbolic architectures? Kind of one of the main tools that are, used in modern neural architectures are convolutional networks, but we think that they're unlikely to be a very good solution, mainly because one of the advantages of the vector symbol, is that its information is distributed, and convolutions are dependent on having local structure and information which can be extracted via the learned kernels. Another thing is that convolution networks often change shape. So you have certain sets of kernels and channels which are scaling up and down and kind of changing the dimensionality of the problem along the way a lot. And so we'd like an architecture which can kind of maintain a set dimensionality through the problem. So what we're showing in this presentation is that we can adapt techniques from residual networks to FHRR symbols to build kind of more powerful, deeper networks that are trainable. And that also the transformers and attention mechanisms that have been kind of taking over tasks like NLP and natural language processing and even image recognition in the previous years can actually have some powerful parallels between vector symbolic architectures and could be highly adaptable to processing them and creating neural architectures that handle them. All right, so now I'll introduce the concept of this residual network for processing FHRR symbols. So to get into the details a little bit of how we handle a neural network that processes FHRR symbols, we restrict the multi-layer perceptron. Just as a simple model, we start out with a multi-layer perceptron and we restrict it to be symmetric so that its output size is the same as the input size. So it's just this autoencoder with a single hidden layer. And so that means that the input and the output are both symbols which can be compared via similarity and bound, and we can keep doing all the vector symbolic operations on them. And now, when you look at the FHRR symbol, each of the values in it corresponds to a single phasor. And when you take the weighted superposition of the complex values those represent and do a phase detection on the output, that creates a nonlinear activation function that's also suitable for backpropagation since it's locally continuous. So to just show how this activation function for the FHRR symbols works, we have these couple pictures below where this represents sort of three input values. You have the angles that are projected out onto the complex unit circle. The length of these arrows is scaled by the weights, which in our work we restrict currently to be real valued. So this just scales the arrows up and down essentially, but it's also possible to use complex weights, which can also kind of move the values around the circle and shift them. But for now, again, we just use real weights. So once that complex scaling and summing is done, you have a new complex value, and you just sort of extend that back out to the unit circle to find its angle, and that's the new value that you compute. And to just go over briefly how this links the FHRR networks to a neuromorphic domain. As any electrical engineer knows, Phasor is linked to a sinusoidal signal, and superimposing these weighted sinusoids and detecting the phase of it is equivalent to the activation function we just talked about in the complex domain. So if instead of having continuous sinusoidal signals, you reduce these down and represent them sparsely with spikes, you can also use a resonate and fire neuron to recreate those full sinusoidal inputs, scale them, and add them up to create a new spiking output. And so this is what allows you to do one implementation of a neuromorphic neural network using the FHRR domain. So this is an example of what it looks like when you do that. Work we published a little bit ago, where you take this real valued input image, you convert it into a FHRR symbol just by random projection, and then you can get this input layer of spikes, this hidden layer of spikes, and the output layer of spikes, and you can this is kind of unrolling it through time. So you can see that eventually the goal that this network was trained on was to produce one output out of phase with all the other possible labels. So it's not really a symbolic output in this case, it's just a simple classifier. And you can see that this network is producing out of phase result on neuron 1, showing that correctly it's digit 1. And running it in the temporal mode, the spiking mode versus the more traditional complex sum and angle only gave very small differences in output for these networks. We only saw half a point drop in accuracy, despite this very different underlying operation mode. And this network was even resilient to kind of random dropout of spikes. So random loss between layers of spikes up to around, we saw we could get rid of around 40% of those spikes randomly before it really started degrading significantly, though more complex networks on tasks like CFAR10 were less resilient overall. So that's just a summary of the neuromorphic motivation of these FHRR networks. So now I'll go into creating deeper networks that process everything via FHRR symbols. And one of the key advances in creating very deep neural networks to process inputs was the concept of a residual block. And this really just improves the conditioning of the network. Everything a residual network can do, basically a conventional neural network without this residual pass can also do, but it's just the conditioning of the function that makes it much, much more trainable to backpropagation. And that's because the default function carried out by a residual block is just the identity function. So if you put an input into a residual block and you look at the output, by default, the random weights will create these on average 0 activations for most networks. And so once you add the original input back in, get output which is very similar to the original input. And so for convolutional networks, this enables the training of very deep networks compared to what were previously demonstrated. So networks with dozens or hundreds of layers were able to be trained using these residual blocks, whereas previously the conditioning of the network was so difficult that backpropagation essentially couldn't do it. So now we have to make a couple of changes to successfully adapt to our FHRR network. So one of the things we need to do is actually add a bias to each of the complex sums that we're doing. Because if you think about coming in with a random input to our neuron, you get a bunch of complex values that center around 0. And so once you take the angle of that, it's actually uniformly distributed around, -1 to 1. And so that gives you an output which is actually very different than 0. So the trick you can do is you actually add this bias to the complex sum step. And so what that does is it essentially shifts the origin of the sum so that by default, it's much closer to an angle of 0. And so this really just moves the output that you get from random weights much closer to 0 than it would be otherwise. And so that kind of takes care of the activation function side of things, but how do we now do the addition side of things that you need for the residual block? We actually replace it by binding, since they're essentially the same thing in the FHRR domain. The binding just keeps it on the correct angular domain. So when you make these two little changes, we actually get this residual block that works on the FHRR inputs. And so here we have this histogram that shows just for random phasor activation values and initial random weights, you get this input and output similarity distribution that's pretty high. And again, we aren't doing anything here that would really impede a spike-based computation, since we've demonstrated you can calculate this activation function with spikes, and other people have demonstrated that you can do the binding function with spikes as well. So now we stack up a lot of those residual blocks, and we show that just for a standard classification task, where you have an input image, you go through 12 of these residual blocks, you get an output that you compare it to a class codebook, and that predicts the class via similarity. You can get around 84% accuracy on FashionMNIST using this very deep network. And if you exclude the residual components, so you get rid of the binding and the bias on the neurons, it essentially doesn't converge to a solution at all. So these residual blocks were very necessary for computing the deeper activation function. I'm sorry, the deeper network. Right, so that sums up the construction of the residual layers. I thought maybe if anyone has any questions, we could get to a couple of them now before we go into the attention mechanisms.
So let's ask the audience. Are there any questions so far?
If not, we can just keep going into the attention section. Yeah. There are plenty of jokes you can make about attention, but I'll try and not make any. So one of the recent advances in neural networks, the past few years, is that essentially people are saying that kind of everything can become transformers. So really, what is a transformer? They're not always as complicated as they might seem. But to give a historical perspective, they really first started playing a role in advancing performance on tasks like natural language processing. So when you look at this example of what an attention mechanism does, when you have a convolutional filter, it learns to associate things which are close in space. So if you have pixels in the input image that represent an edge of something, you learn the filters to extract that in more and more complex ways. But the problem in language is that it's non-local in a lot of ways. So you can have something at the end of the sentence that refers back to the very beginning. And so this local relationships that you have and you kind of depend upon with certain architectures isn't there. And so what attention does is essentially it learns to learn the relationships that can happen even on long temporal or spatial scales by figuring out, given inputs, what relates to each other across these scales and doing it efficiently. So it's really been the key to solving, natural language problems and giving the advances which led to networks like GPT-3 and those other kind of revolutionary architectures. And even, as it's revolutionized natural language processing, people have also started applying it to more traditionally convolutional spaces like image recognition. So here on this figure in the bottom right, we have a transformer-based image classifier, which is competitive with these very deep residual convolutional networks, and can outperform them in some cases. So the heart of a transformer is this QKV attention mechanism. And so what it does is that you have these three inputs, which are matrices. You have the query, the key, and the value. And what it does is, between the query and the key, it can kind of focus on one another. So given these inputs, the query and the key are matrix multiplied. Then they're scaled by the dimensionality of the input. Then they're put through a softmax to produce a set of scores, which is this rectangular matrix over here. And so this kind of represents the relevance between every query that's presented and every key that's presented. And then that is normalized by the softmax and used to scale the value inputs, which kind of represent the meaning of the relevances which are detected. And that's used to create the final output for the attention mechanism. So one of the things I was struck by kind of looking at attention is that the scores we can actually potentially replace by the similarity operation in a vector symbolic architecture. So given this matrix which represents a set of symbols, we have, again, we can create a query and a key, but this time the inputs to both of these aren't just real valued matrices. They're, again, matrices of symbols, which are on the FHRR domain. And then for every symbol in that matrix and the key symbols in that matrix, you can calculate the pairwise similarity, which I call the outer similarity. So for every symbol in those, you get the similarity between each possible pair. And again, that's a value on a restricted domain, which you can use to scale the value of the outputs. You can use to scale the value matrix and produce an output. So we can construct a full self-attention architecture, which is used in the transformer to do, again, the processing of the FHRR symbols in a way that's very similar to a neural network. So to go through step by step, what this little module is doing, you have this set of input symbols in a matrix. They're projected via a single layer to the query, the key, and the value matrices. We compute the attention mechanism we just presented in the last slide on that. That's combined in a residual step. That goes through one more multi-layer perceptron, which is a kind of a standard feature at the end of the attention block. And finally, that produces the output symbol. So this implements this full self-attention module as used in transformers, but adapted to the symbolic inputs. So now we can use this to also do, again, image classification, but in a different way than we did before, since now we're doing it in a way which incorporates attention between the inputs. So instead of taking the entire image and projecting it into a single symbol, we take each column of the input image and project each one of those into its own symbol. So we end up with this matrix here of 28 symbols by the dimensionality of the space we're using. Then, as we just showed in the previous slide, we compute the self-attention between those symbols, and we end up with this matrix which we project down using this output layer. And then we do the same classification step we did before. And this leads to very good results on kind of traditional data sets. MNIST, we get 97% test accuracy, but also for FashionMNIST and Kuzushiji MNIST, we get pretty good 88 and 89% accuracy on the test set. For CFAR10, we run into some overfitting problems where we only drop down to 65% for the test set versus 93% for training. So we need to go back and do some runs with more regularization, which is usually done via dropout through these attention mechanisms. So one of the limits of self-attention, which people have been overcoming lately, is the fact that it requires ON squared computation time with the number of inputs. So you imagine if I tried to do what I just did with these small images on something much larger, because the score matrix we're computing is a square matrix in this case. It scales with number of input elements squared. This computation can actually blow up quite quickly and lead to sort of an intractable problem. So if you go for not just images, but sound and video, it can become computationally prohibitive. So the way people have been attacking this problem is by switching to cross-attention, which is a more novel method where you can use a trainable query. So instead of calculating the query directly from the inputs, you have a latent query, which is learned via backpropagation. And it's only the keys and values which are computed from the input directly. And that switches the order of the computation to being linear now. So it can scale up to the size where you can compute directly on ImageNet images and also kind of video and sound. And it sacrifices some accuracy compared to what you can achieve with pure self-attention where it's tractable. But again, it makes these computations possible in the first place for more complex data sets. So now we implement, again, this cross-attention mechanism with the architecture since it's completely compatible with it. And in this case, we use 32 latent query symbols that we train along with the weights. And we get 86% test accuracy and 89% test train accuracy on FashionMNIST, which is dropping down a couple of percentage points. But there's some hyperparameters you can play with, like adding more latent queries and more training time to get it to be more competitive with the self-attention. And again, the advantage you get with this is the linear compute time with number of inputs that can allow you to process very long inputs using the same architecture. And so what we're really building with all of this is that recently, one of the papers published by DeepMinds demonstrated this perceiver, which is an architecture that applies both self-attention and cross-attention to create this very powerful architecture, which they showed can be scaled and repurposed to process, not just images, but audio, video, text, and structured data. So one of the things they showed is that they can actually use this architecture to process, StarCraft units and data as they used in their RL architecture. And since we've demonstrated these initial results that show that we can create all the ingredients necessary to implement the architecture they showed, that we can, again, create this whole thing out of components that are integratable with vector symbolic architectures and also potentially have neuromorphic implementations. So just to sum up, everything we've been through in the past like 30 minutes, we focused on integrating neural networks with the Fourier holographic reduced representation, and we modified these networks slightly to what we've published previously to allow them to produce residual layers, which allowed these networks to become very deep but still trainable. And we demonstrated that this attention mechanism we could construct then can be based entirely on symbolic operations. And we suggest that in the future, we can use these symbol-based networks to perform the same tasks that were demonstrated by the perceiver IO. And we would like to also demonstrate that all of this is completely spike compatible and potentially compatible with other neuromorphic implementations that may use things like analog resonators or even photonic circuits. So for more details on things I presented briefly, like the bridge networks and the Phasor networks, we have papers of that available. This is just my website where they're all linked at one place. I think we would also like very much to share the code we have for training the residual and transformer networks and make them available to other people who might be interested in integrating the neural networks with their vector symbolic code. I like to give also thanks to my advisor, Maxime Bazinov, and the other members of my lab group. Here are some references, and I'll take any more questions you might have at this point.
All right. Wilkie, thank you very much for your great talk. Indeed, so it's quite impressive what you have shown in the, in the past, in the last slides. I really enjoyed it. Any questions from the audience, please? Unmute yourself and speak up. So let's see.
I'll also have to assume everyone understood everything perfectly then.
Yeah, obviously, or people are confused because of the time change. Yeah.
Okay, I have a question just to clarify.
Mm-hmm.
So these results that you've presented in like the second part of your presentation, they are unpublished yet. Is this right?
Yeah, this is pretty preliminary in that some of the results were from last night.
And that's what I like about our webinars. Last presentation also was of this kind. Okay, but I mean, this last slides really struck me somehow. But I mean, if we just can you comment? How this goes together with this first part of your talk when you presented this bridge network, so the generating the symbols. Maybe right. I have missed it somehow.
Yeah, no, I'd like to connect it back to that. So here, we claim that essentially this is something we can use for cross-domain learning. Mm-hmm. But really, this side of the network is kind of a fake in a certain sense, in that we're just using a code book to convert between a single class label and a symbol. Mm-hmm. And to really demonstrate a true cross-domain learning, we need to replace this with something like audio MNIST, where someone speaks, the phrase 1 or 2, and so we'd really like to match that audio with each image. But the challenge then was to say, okay, given this, audio sample that's 2 seconds sampled at 48 kilohertz and 16 bits, how do we take that and transform it into a symbol in a meaningful way? Mm-hmm. So that's really where I see kind of the cross-attention mechanism becoming very powerful for allowing you to transform kind of large and arbitrary inputs into the symbolic space.
Yeah. So you, in a way, you do not learn the representation, but you kind of fuse different representations, right? Mm-hmm. So in this respect, I mean, so now maybe again, so I need to digest this last part information somewhat more, but did you try using this attention architecture in a kind of autoencoder way? So that's, I mean, you would probably learn latent representations or something.
Yeah.
In this manner.
Yeah. Yeah, we'd like to, replace kind of the it's just autoencoder that we have in here with the more advanced architecture we could construct using attention. I think that could kind of boost the ability of the network to learn more complex mappings between the symbols. I'm not sure, maybe that wasn't exactly what you asked.
Mm-hmm. No, I'm just maybe have some my background thoughts.
Yeah, right now. So one of the key things about the transformer is actually that the output is generally the same shape as the input. So in this case, it's already kind of by a certain perspective an autoencoder.
Mm-hmm. Well, I have another maybe kind of follow-up question. Like you're showing like some of the results you mentioned were on CIFAR 10, and like, yeah, they were not perfect, but like I was thinking in the meantime, is it because basically question, is it the right data set to demonstrate the strengths of this idea that we now can get the symbols, right? Because that might be the issue, right? That the data sets that are sort of standard benchmarks right now, they're not necessarily the ones that would be that would be useful for demonstrating the advantages of sort of processing symbols in distributed representations.
Yeah, I agree with that. Mainly the main reason I use them for these demonstrations is that, in a certain sense, for one thing, they're very well understood by broad audiences, and for a second, they're very easy to integrate into just a simple test to show that you can have complex distributions which are being mapped to one another. But I agree that to show that there's some unique advantage that what these networks can do, so if you have a structured input representing a graph or something like that, that it can process these in a way where you can make some sort of vector symbolic query on it later. That's really what we'd like to move towards, definitely.
Yeah. That's what I was kind of thinking, when looking at your slides, that it's like seems to be a very great architecture, but needs to also be sort of demonstrated on the right problems.
Yeah, because right now we're not demonstrating that we can do anything that a regular transformer or convolutional network can't do, except maybe inherent spike-based implementation. But if you can instead replace this bottom segment here with something like you have a resonator network or something doing something very novel, I think that would be very, the next step to take.
Yeah, that would be neat. Like just to show once you get the output and you do some binding with something else, that wouldn't be a part of your network, for example, right?
Yeah. Yes, it is again why I'm hoping to make this available to everyone, so that if you have an idea of what you'd like to use this for in your own architecture, you can try it out.
Can you maybe briefly, maybe again, I was just missed it during your presentation, this the lowest part of this diagram. So I understand the self attention block that you have described and how you kind of mapped it to VSA operations, but so this class code book, is it kind of pre-generated, or how? I mean, this. Can you just tell a bit?
Yeah, I didn't really mention that. So in this case, it's symbols which are sampled randomly from the domain we're using. So in this case, it's a book of 10 by 1024 symbols, which are just random over the domain. And so each one of those represents the output class we'd like. So then we just compute the similarity between each label that we have and the output of the network to compute the class prediction. So the symbol which is produced by the network that's most similar to the classes is the one that's predicted as the label.
So okay, is it then fair to say that essentially the task of the neural network between the input layer and the output layer is essentially to sort of transfer the image to the correct random vector, essentially, right? Because the vectors you assign are random. So it kind of learns the transformation in a way, right? That takes an input as a starting point. It's supposed to produce the random vector that is as close as possible to the correct one in your code book, right?
Yeah, that's exactly
right. But if code book is randomly generated, so did you check, I mean, the similarity between the produced labels, I mean, this between this chosen vectors? Are they...
Yeah, I mean, since they're randomly chosen, usually they're dissimilar with, p less than 0.0001. So I don't.
I mean, for,
yeah.
for the images of the same type, say t-shirt or short with long sleeves. So, I mean, is it consistently mapped to the same vector from the code book?
Oh yeah. So you're saying like sometimes we have classes which are really closer to one another, right? Like we have the shirt classes and like the shoe classes in FashionMNIST, right? Yeah. And yeah, in this case, the similarities between all of those is equally centered around 0. Since yeah, I think that is a very good question, right? Is how do we come up with maybe these symbols actually deserve to be more similar to each other since they represent more similar things, right?
Because actually that's probably, I mean, this part probably kind of modulated me to these autoencoders. I mean, actually, no, not the autoencoders, but really the part of this variational autoencoders with quantization. So it looks like, I mean, this part looks very similar to the part of that architecture where you do similarity to the Latin space, which is randomly generated, and then so you pick the closest one, and then you use it actually for reconstructing. I mean, for decoding the image.
Yeah.
Yeah, but again, so maybe I'm thinking
yeah, in this case,
in opposite direction.
Yeah, I think it's like in this case, it's less of a latent space at the output here and more of just the output is mapped already to the randomly selected vectors. In terms of creating
but again, I mean, so there is no backprop in this figure, right? So
there is backprop. It goes
from where to where?
So it would start. Yeah, everything is trained by a backprop and gradient descent. So here the loss is computed between the average similarity that you would like. So here, if you end up with an output which is very dissimilar to the correct class label, it goes back through this whole thing. Say, how do we adjust all the weights?
Okay, probably I got it. Yeah, sure. Okay, now I also understand what Dennis asked. Yeah, okay, sorry. I got it. Yeah, so you basically train the network to kind of produce, I mean, to choose consistently one of these random symbols.
Yeah.
Yeah, okay. Interesting. Okay, any more questions? Well, if not, then I would like to thank you once again, Wilkie, for the great talk. So the recording will be available on the website as well as the slide sets. You promised to send me PDF, so I will link it later on. So thank you all for attending today, and see you in 2 weeks from now. So, and have a great time and peace. All of you.
Thank you.
Yeah. Bye.
Thank you.